Okay, good morning, students. Another Monday morning.
Good morning.
Good morning.
How we doing?
All right.
All right, so we had a good week last week. I was really surprised with pleasantly surprised with the results. Everybody more or less came together. Um, so just to kind of show you the plan for the week, uh, we got three sections we're going to cover. We could probably cover them all in one time, one class. It's not really that much. So I'm going to kind of string it out a bit. And that material right there, 10.1, 10.2, 10.3, or the basics of probability and the counting methods, are going to be with with the logic chapter and the set theory chapter midterm. Those things will be on the midterm, okay? All of those three. So this is the new material we're going to cover here. We'll probably get 10.1 and 10.2 today, which is basic probability, and then talking about this thing called the counting principle. All right. Anybody got any questions before we
Sorry, y'all. I just got back. My bad.
get started? What's that?
I had to go do something. I'm sorry. I'm right back.
Okay. All right. So let's just look at the textbook over here. For this material, and then I'll hit my notes in the second hour. Okay, so what we get into in chapter 10, or what we call chapter 10 here, as far as my notes are concerned, is probability, essentially. It's what the entire chapter is about. The first couple of sections after probability, they have to do with these things called counting methods. And what that is it's because we don't always have the ability to see the sample space and count it directly. So what we do is we use these counting methods to count numbers, because for probability, it's not so much what the values are, it's just how many of them there are. So probability is a way to quantify how likely an event is to occur. All right. If we want to find out about rolling a die, we know that there's six sides to a die, and then we roll that die. Well, we can calculate how likely something is to happen. Now, one of the things that I find that a lot of textbooks do is they differentiate between theoretical and empirical probability, but they're essentially the same thing. Okay. It's just the way they're calculated is exactly the same thing. But the first thing we need to know about in order to calculate probability is sample spaces. A sample space is just the total number of ways an experiment can play out. Like flipping a coin, well, there's a head and a tail. We know that ahead of time. We can't predict which one it'll be when we flip the coin, but there's two sides. Rolling a die, there's six sides on a die. So 1 through 6 for each one, for a side with a 1, a 2, a 3, a 4, a 5, and a 6. Those are make up in the sample space. Drawing a card from a deck. There's 52 cards in a deck. All right. So the probability experiment is just a process that gives us a well-established result. Like I said, is 2 sides of the coin, 6 sides of a die, 52 cards in the deck. Okay. So like on a coin, you got 2 sides, a head and a tail. All of them do to some extent. They're just a little bit different. The die has 6 sides. And you can see here. If we flip one coin, we got a head or a tail. It's the sample space. We don't know which one it's going to come out to, but we know it'll be one of those two, a head or a tail. With rolling a die, 1 through 6, we don't know which one when we roll. It will be one of those, is what we know. If you got a true or false question on a test and you don't know the answer, you're guessing, then there's 2 possible outcomes, true and false. And then if we flip 2 coin, you can have head, head, tail, tail, head, tail, tail, head. Very similar to what we were talking about in the logic when we had the permutations, 8 rows, 4 rows. Each one of those are different. And we're going to find out about that. So the experiment is just anything like rolling a die, flipping a coin, pulling a card, any number of things. That's an experiment. And we know exactly what it could come out to, not what will happen exactly, but what possible outcomes there will be. And an event is just a subset. And again, we're going back to the idea of chapter 2, subset. It'll be some part of what exists in the experiment is an event. We could say rolling an odd number on that die, rolling an even number, rolling a number greater than 5. We could break it up any number of ways. So the only thing that we really know as far as theoretical and empirical probability is concerned is theoretical probability is kind of exists in nature. If we have a coin and we flip it, we know that the probability of the head is 1 out of the 2. We know the probability of the tail is 1 out of the 2. Okay? It's just the nature of it. Now, empirical probability is counted as it's the same exact formula as we'll see for empirical probability. The denominator is always the total. Let me write that down here. Okay. So the denominator is going to be your big number. And what this amounts to is this is what makes it a fraction, essentially a probability is always going to be a fraction. It can simplify and become 1 or 0, but it'll always be between 0 and 1 inclusive. It can be 0, and we'll see what that means. And then we'll see what a probability of 1 is. But the numerator then is the total number of outcomes. In other words, it's the subset of those values defined in the way that we want to see them successful. In other words, odd numbers, even numbers on the die. So the large number is always the denominator, because that's the only way we're going to keep that fraction. And a fraction, or I'm sorry, a probability is always going to be a fraction between 0 and 1. It can be 0 and 1, but it can't be greater than 1, and it can't be less than 0.
Look, I don't know about y'all, but I'm lost. So I don't. I'm totally lost.
Well, when you say lost, what do you ask me something then?
I I don't know what the question to ask. Like this problem in front of us, I wouldn't even know.
Well,
I
I
know
haven't done any. I haven't
looks.
done anything yet.
Yeah, we're gonna
No,
need
no problems.
yeah, we're gonna practice this a lot more. So I just
Yeah, we're
looks like
gonna.
gibberish.
Yeah, that's what the second hour is for. This is just to get us used to the concepts.
Right,
Okay.
right. It's just we're gonna have to work it out a lot because it's gibberish to me right now.
Yeah, let's just look at the definitions. That's all we're really looking
Right,
at.
I appreciate it.
All right. So again, you can just call it computing theoretical probabilities. Usually refers to things like dice and coins. So look at this. We got one die there. It's got 6 sides. You got a 1 on one side, a 2 on the other side, a 3 on one side, a 4, a 5, and a 6. So let's say we want to find the probability of rolling a 5. Uh-oh, what happened?
This sounds like something you use in gambling, like
Yeah,
like
you
you know.
can. Yeah, that's what gambling's based upon. That's how the house knows how much money they're going to
Yeah,
make.
right. It's nothing but statistics and probability. You know?
Right. What happened to my, there we go. All right, hold on, let's see. All right, so what happened to my, hold on a second. There we go. Okay, so let's say we got that die and we want to find the probability of a 5. Okay. So the probability of a 5 is equal to number of 5s on die over all right. So how many sides are there on a die?
6.
Yeah, there's 6 sides on a die. So how many 5s are there on the die?
1.
Yeah, there's one of each. 1, 1, 1, 2, 1, 3, 1, 4, 5. So the probability of a 5 is 1/6. Okay, so there are 6 numbers on that side of the die still. And how many of those are odd?
Three?
1, 5, and 3.
Yeah,
Right.
it'd be three. It'd be three.
Okay. I was wondering if I was going to need to bring up a die, but I think most people know it. So 3, 6, and then that simplifies down to 1/2. So the probability of getting an odd number is 1/2. The probability of getting a 5 on one roll is 1/6. So that's the
But
nature of
right,
probability.
but ultimately, the probability it'd be 50-50 rolling dice. You either gonna get your number or you're not.
Yeah, but you're using the 50/50, like each one is going to have 50% chance of coming up. Each one
Right.
will have, look, if
Well,
there's
what,
only 2 sides, then yeah, it would be 50%. But
what we're trying
one,
to determine in this class is like say the probability of you're breaking it down. So the probability of you getting one is what?
the
Um,
probability of be getting what
one. Like
on
the
that
no
die?
yeah.
There's only one on there, so 1 over
Correct.
6. So it's a little
One.
over 17%.
Right. You can convert 1/6 into percent.
0.1666,
Yeah,
yeah.
yeah, 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 yeah. Okay, got it.
See if you multiply by 100. See, that's 16.7%.
Sure is.
So
Never thought
that's
about it
how,
like that.
yeah, I mean, that's one of the things that you're going to see, especially in this chapter, about decimal versus fraction versus percent. There'll be changes in between those. So as I had said is, if we take that 1 and divide it by 6, so that's approximately equal to 0.17 or 17%. So those things all mean the same thing, okay, as far as probability is concerned. All right, that's the fractional amount, 1 divided by 7.
It's actually pretty interesting. I didn't know. I didn't
Mm-hmm.
know. Didn't even think about it like that.
So 0.17 or 17%. And of course, it's rounded off to the second decimal places. Now, 1/2, that is your 50/50, because with the coin, there's only 2 sides. It's going to come out to one or the other.
Right.
So 1/2 is 0.5 or 50%.
So you're saying it's 50% chance you're gonna land on an odd number?
Exactly.
Right. And so in 50-50 on even number.
Mm-hmm.
Yeah,
Exactly.
makes sense. Okay. Thank you.
See, in 1 divided by 2, that's the 0.5. And then you multiply it by 100 to get your percent. right. So the complement is something we're going to use again here. So don't forget about that. So the complement of an event, or the probability of the complement will be just 1 minus whatever you got. So let's look at something here. All right. Of the next 32 jurors on the docket in a county court, 5 are homicides, 12 are drug offenses, 6 are assaults, 9 are property crimes. If jurors are assigned to trials randomly, what's the probability that a given juror won't get a homicide case? Find the probability using both the formula for theoretical probability and the formula for complements. Okay. So, isn't a drug offense. All right. So there's 32 trials. 12 are drug offenses. So the probability of drug, we'll just say, is going to be equal to, and there's 32 of them. And then, so 32 total, 12 drug offenses. So we can simplify it. So 6 3/8. So there's the probability that we get a drug offense. But they want to know, isn't a drug offense. So using the complement rule, all right. And so when you're using the complement rule, there's a real easy way to do it without having to go through and convert this. This should be 1 minus. So 1 minus 3/8. So 3 from 8 gives us 5. That's how you can easily find your complements. Whatever your denominator is, subtract the numerator from it, and what's left over is your complement. So this is the probability that it isn't a drug case, is 5/8. We can also look at it as a decimal. So 62.5%. So there's your decimal. So that's the basic of finding a probability. All right. So and it's the same number of, it's the same denominator for empirical probability. Like I said, yes, I don't even think they mention it in the Newton. So it's all probability is done the same way. Total on the bottom, and then the numerator is the subset of whatever you're looking for the specific event. All right, let's look at the counting principle. All right. So the fundamental counting principle is a way to find out at a glance how many different ways there are to do things. If you've got 2 events and there's a particular number associated with that number of events, and then the other event also has a number associated with it. Well, when you combine those 2 events, you can find out how many different ways there are to do it by multiplying. This is one that I've got in my notes. But if you've got a couch or want to pick out a couch and the 2 finishes are leather and microsuede, and then you can have 4 different colors. Well, how many different couches are there? Well, there's 2 here and 4 here. So 2 times 4 is equal to 8. All right, and you can see right here. So it would be LT LW LR LG. Leather tan, leather white, leather red, leather green. And then over here, it's going to be the microsuede tan. The microsuede white, the microsuede red, and the microsuede green. Okay, so that is 1, 2, 3, 4, 5, 6, 7, 8 different or 8 distinct couches. By taking the 2 different types in the first group, the finish, the leather versus microsuede, there's 2 of them. Oh, and I should have put 4 here. And then 4 is for the coloring. The coloring, it's repeated. So that's why you end up with 2 times 4, or 8. 1, 2, 3, 4, 5, 6, 7, and 8. Okay. It doesn't have to be just 2. You can do it with 4, 3, 2, any number of groups. So in other words, all right, so here's a good one. All right, a paint discount or a discount paint manufacturer plans to make several different paints. So they got colors: red, blue, white, black, green, brown, and yellow. 1, 2, 3, 4, 5, 6, 7 different colors. 2 different types: latex and oil. Texture is flat, semi-gloss, high gloss, and then the use is outdoors and indoors. So how many different kind of paints can be made? Well, you got 7. You got 2. You got 3. And you got 2 types. Seven times 2 times 3 times 2. What is that? Let's say 14. 76. 14 times 2, 21. Let's double check it. 7 times 2 times 3. 84. Okay. So 84 different types of paint. Because what this is giving us, it's giving us a red latex, a red latex flat, a red latex outdoor, a red oil flat outdoor, and so forth. So 84 different types of paint. You can use it like with ID cards and stuff like passwords. It's neat. So if we've got we're going to be able to use the letters A, B, C, D, and E. So 5 different letters in a 4-letter card. How many different cards are possible if letters are allowed to be repeated? All right, and it's different if it's repeated. So there are 5 different spaces, and each time, so for the first letter, which is what this one is, A, B, C, D, and E are available. The second spot for the code, we still got A, B, C, D, and E available because repetitions are allowed. A, B, C, D, and E, again, 5. And then for the 4th letter, there's 5 choices. So that ends up being 625 different choices for the letters for that password. Now, if we cannot have repetition, then it's slightly different, because for the first time, we've got A, B, C, D, and E. All right. But once we use the first one, A, okay, it's gone. Okay. Because we can't repeat it. So then we've only got 3. And that's what that, I'm sorry, it's only 4 left. There's 5. So the first one's got 5. Then after we use the first one, then there's 4, B, C, D, and E. When we get to the third one, there's only C, D, and E left. And then for the last one, only 2 left. So when we repeat, we don't have to subtract out. But when we repeat, we subtract 1 out. So this is repeating. And then this is no repetition. So repetition allowed, no subtraction, okay? In other words, you're using those same 5 letters in each, or you're open to use it in each of the 4 spots. But when we have no repetition, then once we use all 5, there are only 4 left because we used one. Once we use those 4 and no repetitions, there's only going to be 3 left. Same thing on the next one, only going to be 2. So let's look at this right here. All right. So lock on a storage facility is controlled by a keypad containing the digits 1 through 5. So we're doing 3 codes, 3-digit code. All right. They can be repeated. So 1 through 5 are possible there, here, and here. If they cannot be repeated, then we're going to subtract. So for this one, 125 different. And then let's see, what's this one going to be? 60, I believe. 5 times 4 times 3. Yep. All right. And then this last thing, the factorial notation. All right. On most all scientific calculators, and probably even most other ones, you've got this right here. That's called the factorial key. Now, what that means is essentially whatever number you put in for n. So let's just say we're going to put in 1, and then we'll hit that key. Well, it's just 1, because all it is just we're counting down and multiplying. So 2 factorial is 2. Why? Because 2 times 1 is 2. Oops. 2 times 1 is 2. So you're just multiplying down. So 3 factorial is 6. How do we get that? It's 3 times 2 times 1. So that's what the factorial key means. So inside of your calculator, I believe this is the same thing, your calculator, you got it's buried under the PRB button, but it's there. We'll learn about the other. There's 3 things under the PRB button. There's the factorial, and then there's the permutations and the combinations, and we'll get those a little bit later. So most of these can be done by just clicking that key. So for example, on this, six factorial, 720. So these numbers get big pretty quick. So that's 6 factorial, and at the bottom, 4 factorial. So this would be 30. See how huge a number it gets real quick. All right. And so permutations are when we consider order important. So if we got distinct objects and we're worried about specific order, then it's called a permutation, because with a permutation, order is important. All right. And so there's a formula for it. We'll see it later. And then there's the other one, which is combinations. It must be in the next thing. We'll worry about that. So coming up at 11:45, you should be able to see that little in-class assignment thing. You can have the rest of class period to work on that. So it's to do with what we just did, the basic of probability. So give it a try. If you got any questions, give a yell, all right? Still got a couple more minutes before it shows up. All right, you should be able to get in it now. Just let me know, yell out if you having any issues, okay?